Okay, so we're going to continue talking about variational problems. And see how much we can do. But so let me remind you really quick what the setup is. So the setup is to minimize a functional, that's a function of functions, if you like, which also has to specify what is the set of admissible paths or functions. Okay, and let me be very clear here. We're going to consider that this is a function of one variable, x, in some interval. So that would be, I don't know, one-dimensional independent variable. So for that reason, we think of this u as paths. Now, we'll talk also today about. So yesterday we talked about functions that take only real values, so you can just plot them. So for instance, u is scalar, so then you really can do you can visualize u as being some sort of path in the plane, right? But we'll see also that u can be n-dimensional. So still a function of x, which we're going to restrict it to be one-dimensional. So x is still an interval, but in that case, this is going to be thought as a path in. It's also a path, right? It's a path from a point in Rn. I don't know. Let's think of it like this. So this is say R2. Then it's going to be, a point here and to a point there, but this is A and this would be B, right? So it's really a path in Rn plus 1. Okay? And it would still have prescribed, well, you can have prescribed both endpoints, one endpoint, no endpoint. You can have other restrictions, as we'll see in a second. Okay? So, and how do the functional look like? So the functional to be minimized looks like an integral with respect to x over this interval, and it has some integrand that may depend on x, may depend on u of x, may depend on u prime of x. Okay? Okay, later on you can actually include second derivative of u and so forth, but if you think of u as being sort of a real trajectory in Rn, maybe I should put the Rn here instead of R2. Then this is probably one of the most physical relevant situation where the integrand may depend on, this would be the time. So it may depend on time explicitly, it may depend on the location of that path, right? It may depend on the speed of that path, right? So in the case, really this this formula is true for 1D as well as for paths in U may have several variables. So for instance, if U is a scalar function, then that's what it looks like, or U may be a function. Well, maybe let's just do it like this. So if n is greater than 1 and U is a function defined on interval AB but with values in Rn, so U would be U1, U2, Un, then this really would mean could be a function of x of U1, Un, and U1 prime, Un prime. Okay, so that's what you could have. Okay, so we're going to always write the function like this, but we may think of U as being vector or scalar. Okay. Now, the next step would be to think of x as being several variables, not just on an interval. And that's where the book has that sort of gradient, because then you don't have the derivative, you have the gradient with respect to x, right? And then the Euler-Lagrange equation would have to be modified accordingly. But if x is one variable, the Euler-Lagrange equations look as follows. And I'm going to write it in the following form. I'm going to, instead of introducing lambda and xi, which they have a reason to be there, but let me write it like the following way, so to see how easy it is to kind of expand to n dimensions. So this would be the partial derivative of f with respect to the second variable, right? Minus derivative with respect to x. X is one dimensional, so it's just plain derivative of f sub partial with respect to third variable. Okay? And of course, these things are evaluated at the specific argument, x, u, and u prime, right? Okay. Now, what happens if it's n-dimensional? So this is, so if u is just scalar, then we have one equation, right? But if u is a vector in Rn, then the Euler-Lagrange equations is not an equation, but it's a system of equations. N equations. And right, just look at this. You know, f would have several arguments, right? So the Euler-Lagrange equation would translate in the following. Would be f sub ui minus derivative with respect to x, f sub ui prime equals 0 for I equals 1 through n. Okay, and why is that? Well, you could kind of imagine how we derived this when u was just a scalar. We said that corresponds to the derivative in the direction of a function phi, and that was a scalar. In the case you have a vector, you would have to consider u plus t phi, where phi has n components. When you redo that, basically replace u with u plus t phi, and you take the derivative with respect to t, set it equal to set t equal to 0. This is what will come out. You'll have a system of equations. Okay. In physics, this is kind of used a lot. Many times x is really t, because that's time. The position is usually called xi, and the derivative of the position would be the velocity or the momentum, and they're called pi. Okay, just in case you've seen that in physics. So in physics, so x is like this, and of course x can be x1 through xn, and one uses excuse me, not pi is still xi prime, xi dot. They use xi dot there to say this is 0. Okay. So let's see. What we're going to do now is kind of see some specific cases when this variational problem is relevant. So, and I'm going to start with a physical application. That is basically motion according to Newton's law of motion. The mass times acceleration is the force applied. Okay, and so the first application is in Newton's law of motion. And a conservative field. Okay, so what is that? You very well know that if you have a force applied to an object, of mass m, then that object will actually have an acceleration m times a equals the force, right? And the acceleration is the derivative of the velocity vector, right? And the velocity is the derivative of the position vector. So I just mess this up here. So I'm going to sort of for a while talk about x being the position and t being the time, right? This is the velocity. This is the acceleration. Okay, and what does it mean that the force F, the force field, so we have basically a force that acts at every location in the space where the motion takes place. F, we say that F is conservative if F is the gradient, or there's a reason why I put minus gradient of a so-called potential function. Does anybody remember from Calculus 3 why is this called conservative? Why is the gradient vector field, right? So if I have a potential function, u is a function of x. So u is a function of x, right? Think about R3. And I consider this gradient, opposite or not, doesn't matter. Why is this called conservative vector field?
The work is path independent.
The work is path independent. So the line integrals of this force, basically the work done by this force along any path is independent of the path, is only dependent of the endpoints of the path. Another way to say this is, if I take closed loop, the work is zero. So basically, wherever the work was positive, there's compensation. So in the end, the total work over closed loops is zero. And that basically corresponds to conservative vector field. And an example that you have to think in mind is the gravitational force. So for instance, gravitational force is think of it as G. Yeah, it's a constant. J, if you want. Okay, so if I have, or K, if in R3. Yeah, let's think about it in R3. R3 or R2 is the same. Let me just stick with R2 for now. So I and J is the vertical direction, and the force is actually negative mj. That's the acceleration is constant, right? So the force would be minus mg. So why is this conservative? Because you can write u of x to be minus mg x2, I guess, right? If you take the gradient of this, the first component is 0, the second component is minus mg. So it's exactly that. I mean, the potential is not unique. You can actually add a constant and have the same relationship. But this is one of them, for instance. Okay, so the question that we have is, how can we describe the motion? Starting with this Newton's law of motion in a gradient, or in a conservative vector field.
Take it around, you mean plus mgx, right? It's negative 3.
Yeah, thank you. Yep. Right. So basically, it says that the potential is increasing as you go up, and it decreases as you go down. Yeah, thank you. Okay, so the claim is the following, is that MA equals F equals this particular F, that's conservative. So that is my opposite to gradient of a potential function, is the Euler-Lagrange equation or system for the functional and we use L actually here it doesn't matter, it's just the functional I given by the following. So it's the following function of x and x dot, x prime, well, dt. Where L has this specific form is, let's see, m length of x prime squared over 2. Now this in physics is called the kinetic energy. Okay? Minus u of x. Okay? So if you construct this function, you know, and again, it may sound like you know, it's just artificial, but think about, you have on each path, you know, you assign this scalar number, right? So take a path in Rn, right? Take the derivative, length of the derivative squared, like this, right? This will depend on t, where it's evaluated, but we integrate with respect to t, and that we call it to be the functional. Okay? This is called the Lagrangian. And I think it's the integrand that's called the Lagrangian, isn't it? Functional. I'm sorry, the Lagrangian of the along the path x equals x of t. Okay? So basically, this will be sort of a function of t that's along the Lagrangian. The corresponding, it's on page 152, but it's a little bit different as far as notation. So if you look at 152, you'll see the psi's and the lambdas. So I wouldn't really say you should follow that, because you might get confused. So just think of that, you know, of this expression you integrate, and the fact that the Newton's law of motion is saying, well, as we'll see, it's actually the Euler-Lagrange equation for this functional might say that if you want to minimize this integral, then the minimum is going to achieved basically where the motion is going to take place. I mean, the motion is going to take place at an optimal path for minimizing this functional. It will be sort of called the principle of least action. You want to have, so this would be sort of the action along that path, right? Say you fix 2 points, and you say, I want to go from this point to that point, and have the least action. Action meaning that functional, right? Well, the optimal path will be a potential minimizer, right? So if somehow you say there is a unique minimizer, well, that's going to be the motion that's going to take place. I mean, ma equals force. Okay? So why is this claim? So if you start with this functional, how do you actually get the Euler-Lagrange system or equations? Well, you take the partial of of this integrand with respect to x, each x, right? So the Euler-Lagrange says this, right? Well, what's the derivative of L with respect to, say, x1, the first component of x? x1 doesn't appear here, right? In the first. It only appears in the second one, right? So this basically says, so let me write it. Lxi is partial of L with respect to xi, and this is minus partial of u with respect to xi. Yeah? Again, L is given by this, by that formula, right? So the partial with respect to the first n components is only hitting on the second one, right? Because the first one doesn't has xi in it, it has xi prime. Okay? Those are totally independent variables. And L xi prime, that also will have to be differentiated with respect to t. But before differentiating, what's the derivative with, say, x1 prime? Well, there's no x1 prime in the second equation, in the second part of the Lagrangian, right? In the potential. But it is in the first part. And how do we differentiate that? Well, the length square is basically the sum of the squares of x1 prime, x2 prime, x1 prime. So this is going to be just m xi prime. Right? There's a 2 that gets simplified with the 2 in the bottom. So what's the Lagrange, the Euler-Lagrange equation? It's going to be minus partial of u with respect to xi minus derivative with respect to t of mxi prime equals 0. And remember now, these things, so once you do this kind of formal differentiation, now you have to go back to evaluate it along the path. So now xi prime becomes xi prime of t, and so it basically is the second derivative of that. So you see, mass times acceleration is the force, because force is a gradient of u, minus gradient of u. Okay? So again, basically Newton's law is just, can be rephrased in saying that from going to point A to point B in a conservative vector field, this is achieved by minimizing the action, that is the integral of the Lagrangian, right? And it may be just sort of a nice or kind of curiosity, but there is actually some very important implication of this. And the implication is that, so consequence of this fact is that along each path, basically satisfying the Newton's law of motion, the total energy, and I'm going to define what that is conserved. The energy is defined by this h instead of L, and it's given by mx prime squared over 2 plus u of x. So again, take any path, right, between 2 points, say. You can compute this. It's going to be a function of time along that path, right? Well, what this statement is saying is that along the optimal path, this quantity is independent of t. It's constant. And if you think of this as kinetic energy and as the potential energy, it says that the sum of the two stays constant. Okay? Okay? So the first time you see this, and that's kind of a principle that everybody says if there is no friction, there's no energy loss, right? But if you think about how to prove such a thing is, could be a little bit daunting. I mean, not that it can be done, but you can do it. But what I want to show you is actually how this actually follows from this Lagrangian, or how from this principle of least action. Okay. So here's a fact, general fact about Euler-Lagrange equations for a general functional. Where L is basically a function of two variables only, not a 2 or 2n, depending on, but there's no t dependence in this case. Okay. What can you do about this? Well, let's just rewrite the Euler-Lagrange equations. This is L, X, and now xi or x, just think about, I'm just going to write like this, but okay, so I want to actually evaluate this at x of t and x prime of t minus d by dt L x prime x of t x prime of t. Okay? If that's the case, x is either vector or scalar, doesn't matter here. And this is equivalent to the following. Basically, you can write this as a derivative of some quantity, and the quantity is the following: is L. I'm sorry. Yeah, it's just L at x and x prime minus x prime of t L x prime at x and x prime. Okay, so let's see, why is this equivalent? Well, it's simply as taking the derivative with respect to t inside, right? So if you take the derivative of L, what do you get? You get L sub x times x prime, right? I'm going to suppress the arguments for L. Plus L sub x prime, x double prime. That's product. There's the chain rule in the first one. You take the derivative of the first one here. So it's going to be the partial of L with respect to the first variable, L sub x, times the derivative of x with respect to t, right? Plus partial of L with respect to second variable, x prime, times x, the derivative of x prime, x double prime, right? And now let's do this as a product rule, right? So I'm going to take the partial of this, so it's going to be x double prime, I'm sorry, not just the partial, the derivative of x prime, so minus x double prime, Lx prime, minus x prime, the derivative with respect to t of Lx, with the argument. What do you see here? This and this cancel. And what's left is x prime times Lx minus derivative with respect to t of Lx prime. Okay? And this is 0. Okay? So again, how do you get from Euler-Lagrange equation to this? It's simply multiplying both sides by x prime of t, and then adding and subtracting this term, and then recombining the derivative to look like that. Okay? As a consequence, the Euler-Lagrange equation in this particular situation can be written as just this expression is constant in t, independent of t. Okay? So if L is just a function of two variables and not three variables, in other words, there's no t explicit dependence, then Euler-Lagrange equation can be written as L of x of t x prime of t minus x prime of t L sub x prime x of t x prime of t equals constant, because the derivative is 0 with respect, so that's a constant, right? Well, if you go back and plug in this in the in the Lagrangian, so if L of x and x prime is m x prime squared over 2 minus u of t of x, then h of x, then the Euler-Lagrange equations for this look the following way. So just L, so m x prime squared over 2 minus u of t, or u of x, minus, so this is just L, right? Minus x prime times the partial of L with respect to the second variable that we computed. It's mx prime, right? And basically we know this is a constant independent of t. Well, just look at the first and the last term. This gives you, this is 1/2 minus, basically 1, it's basically minus 1/2 m x prime squared minus u of x equals c. Okay? So it means that what we call h we just call it with plus, is constant, independent of t. Okay? So that says the energy, the total energy, the kinetic energy plus potential energy is conserved. Okay. So that's one property that's kind of important and follows from this Lagrangian formulation. So basically, thinking of the mass times acceleration equal force as being the Euler-Lagrange equation for a minimization problem. Let's talk about, so just for your reference, I mean this, part of this is described here at page 152, but the notation is, I mean they use t instead of x, so that's what physicists would use. They use u instead of our x. Okay, so they keep u as the path, and u prime would be the velocity. Okay. But notice that the notation can be, I mean, are we talking about one dimensional or are we talking about n dimensional? You know, you can keep the same notation and just interpret, like here, the length, I mean the norm, the bars represent, in n dimension would represent the length of that vector. Okay, so let me talk about the one very famous variational problem, the Brachistochrone problem. (145). So we're kind of going a little bit back and forth, but this chapter is so huge that we're not going to be able to cover the whole thing. So the Brachistochrone problem and the etymology is from Brachistos, which says the least, and Chronos is the time. So basically the problem is the following. It says that in the gravitational field, constant gravitational field, so we're not talking about extraterrestrial, just like at the surface of the Earth, say, where the gravitational field is constant, you have 2 points. You know, they could even be at the same height, but you have 2 points and you'd like to kind of let one particle go from point A to point B, and you want to know what's the least amount of time that it takes. Okay? And you might even kind of visually guess that you have to take some sort of a route that's not a straight line. May not be a straight, and it's not going to be a straight line. Certainly, the paths that, you know, a path like this would take longer because, well, we'll see why it takes longer. But you can kind of sense that it might be very slow here, so you may spend a lot of time before going down to B along this path. And what is actually, what determines that time is basically the velocity. I mean, what's the velocity of such a particle along a path? Well, here's where we're going to use this total energy being conserved. So we're going to say that, so let's call V to be the velocity. So this is an R2. We're talking about R2 because, R3 is the same. Doesn't matter. You take 2 points, you can find a plane, vertical plane, in which to have the motion. So let's talk about, the derivative of the position as being the speed, if you want, right? So this is the speed at a given time. Then what do we know from the total energy conserved? Some of the kinetic and potential energy is constant. And we actually know what the potential is mgh, right? Where h is the height. So let's call that vertical axis h, for instance, right? So there's the second component of x. There's a horizontal component, there's a vertical component. So the vector x is, I don't know, displacement and height, okay? So what is that thing saying? It's saying that if initially you have some speed, right? But actually think about it in the following way. Think about it. Initially you have 0 speed and certain height, right? Then you're going to gain speed if you decrease the height, right? But if you, for instance, try to go along the other path, that is, go back to a similar height, then you're going to get 0 speed again, right? So the idea is that you want to decrease your height fast enough, right? So that you increase the speed fast enough so that you travel less. The problem is, the length, if you decrease the height too fast, right, you're going to go a longer distance, right? So we saw last time, we saw the shortest distance is along the straight line. But if you go along the straight line, you may actually, you're not increasing your speed fast enough, right? So clearly that there is somewhere in between, like an optimal path along which the time it takes. So I guess I didn't say what the optimization problem is. Is find the path between 2 points A and B, along which a particle travels the least amount of time in the gravitational field. With no friction. So we're talking about an ideal situation in which there is no friction, so there is no other force. This is the only force that acts on the object, right? Okay, so so think about h, even h equals 0, and you start with velocity equals 0 at a. So without loss of generality, we're going to assume that the height at point A and velocity both 0. Okay? Then we have that mv squared over 2 plus mgh equals 0. So that gives you sort of a formula for the velocity. Not for the velocity, for the speed. Okay, so this is the length of the velocity. It's not the actual velocity vector. It's just the length of the velocity. Okay, to be given by this formula. So again, here the height would be sort of the starting at 0 and going negative, right? So you have the velocity, the square root of that quantity, and that's well defined. Okay. So how do we set up this as being a optimization problem? Well, we'd like to express the time traveled from A to B along a path, let's say x is x of t. Okay, so this time is going to be computed the following way. It's going to be taken to be sort of infinitesimal. You add the times it takes let's think about it like this. If this is the arc length, so the arc length is sort of the infinitesimal length on that path, right? And you have velocity or speed, that's the speed, the length of the velocity equals v, right? Then the time it takes is the distance divided by the speed, right? If that speed was constant, right? But because it's not constant, you're going to have to integrate along the curve, right? Let's call it curve C. So that's pretty much a line integral with respect to the arc length. That's again, ds is the arc length. You must have seen this in Calculus 3, but you probably forgot how it's done. Well, how it's done is basically ds is replaced by the length of the position. So this is the square root of x1 squared, x1 prime squared, plus x2 prime squared. Okay? And for v, we computed from above what v should be. V should be, and v is the square root of 2g x2, I think. Okay? X2 is the height, right? X2 goes, say, up vertical. Well, think about x2 going horizontal. Upside down from the height. So that's the system in which you actually describe that motion. So it starts at A and it goes down. So you don't have the minus there, right? So this is the point A, and there's a point B here. Okay. All right. And now finally, the other thing to say is that one can parameterize the curve C such that x1 is just t. So you can always parameterize a curve. Well, not always, but you can parameterize. Well, you can only consider the curves that can be parameterized by, x1 equals t, and x2 is a function of x1, pretty much, right? So, anyway, in the end, what you end up with is the following. You want to minimize the integral of this square root of 1 plus x prime. Let me use u because they use u in the book, so let me use u here. So u prime. They use u or t? Sorry. They use y. Okay, so let's use y here. Nah, they use x. I'm going to use t because it's. Hold on a second. Yep. Yeah, it doesn't matter. So it's going to be divided by the square root of, forget the 2g, just y of t dt. And this is from A to B.
The book has x.
There's x everywhere. Okay, so but the variable, the integration doesn't matter, right?
It's where t is at the bottom. This is the way they have it.
It would be your x1 term. That top one?
Yeah, it's the upside down. This should be the upside down. So this is, okay, this is the y of t, and this is the t. Is that? Okay, so the parameterization is the other way around. So you parameterize. Yeah, I should use x and y of x. Oh, I don't know. So subject to y of a is, so that would be, that would be the displacement sort of. So this is y1, in this case is 0, and y of b is whatever this distance is here. So this is, and they use b. Let me call this little d. So that's the distance traveled along horizontal line. Yeah, okay, so I mean the only the thing that we shouldn't have really done is write the arc length in terms of t, because t would be the time traveled by this particle. So it's kind of we should have used a different letter here, and I think using x would have been better, but might have gotten confused. So let me put like a t prime or a t. T prime everywhere. So that's okay. So this is really along the renaming t prime equals x. So that's the vertical coordinate, or the height. You have to minimize the integral over the height, of the square root of 1 plus y prime of x squared over square root of x dx. You really start at 0 and you go to some number b, let's say b here, okay? With y of 0 is 0, y of b is the horizontal displacement, okay? Okay, so what is the functional here? Well, this time the functional only depends on two variables. One is the independent variable, so that's the integrand, right? The integrand is the square root of 1 plus y prime of x squared and square root of x. Right? So what's the Euler-Lagrange equations? There's only one equation, right? So it's basically saying f with respect to y, that's 0, right? Because y doesn't appear explicitly. Minus derivative with respect to x of f with respect to y prime. Okay? Is 0. But partial with respect to y is 0 because f does not depend on the position explicitly, right? It only depends on, well, the position being, it's kind of hard to name y being the position, but it only depends on the independent variable x and the derivative of y with respect to the independent variable x. And what's f y prime? I think we did this last time. It was y prime divided by the square root of 1 plus y prime squared. And of course, with the square root of x stays, as a constant, right? You take the partial derivative, so that's okay. So the Euler-Lagrange say the derivative with respect to x of this expression is 0, which means that the expression, the partial of f with respect to y prime, is constant, right? So, moving the square root of x c squared of x to the right side. And now what's the goal? The goal is to find y prime, right? Remember when we talked about the shortest path, the shortest distance, the shortest length, we didn't have the square root of x here. That's the only difference. Now we have the square root of x. So this guy is, you square both sides, c square x, and then you solve for y prime squared, so it's c square x 1 plus y prime squared, so it's linear in y prime squared, c square 1 minus c square x, okay. So y prime is basically the square root of c square x over 1 minus c square x, and y of x by integration is the integral of this, so it's the square root of c square x over 1 minus c square x dx. Remember, the derivative is with respect to x, so the integral is going to be with respect to x as well. And the limits are 0 to, well, really, it's the improper integral. It's the indefinite integral. If you want to put a proper integral, you'd have to change y of x is the integral from 0 to x of square root of c square s over 1 minus c square s ds, right? So that's the formula you have in the book. The only difference in the book is they use a different constant c. I think they use the reciprocal 1 over c. So you can write this as the integral from 0 to x square root of s over 1 over c square minus s ds. Okay? But who's going to determine the value of c? So the value of c is determined by the condition that y at b is a certain value, right? Whatever the second point was. The first point we picked it to be in the origin, so the second point has some coordinates. And I guess you could stop here, but it turns out that if you go a little bit further and try to look for the shape of that curve, because we still don't know, right, what the shape of the curve is. Of course, if you integrate that explicitly, you would actually figure it out. But there is a smart way of actually parameterizing this curve. Instead of thinking of it as a graph of a function, you just find a parameterization. So that's basically done the following way. Maybe I'll skip. It's actually this change a variable. S equals 1 over c 2c squared 1 minus cosine of r. So that's 1 over c squared sine square of r over 2. So there would be a trigonometric substitution, which what would give you in the denominator here would give you cosine squared, right? 1 minus sine squared, cosine squared. And the top it would be sine squared over cosine squared, tangent squared. Theta squared would be just tangent, right? And then of course something by differentiating s so you get rid of the square root. That's the important thing. You'd also get rid of the fraction, right? So it would be just a change a variable in the integral, and what you get is the following. So you get the y of t to be c squared, well, I'm using the 1 over c, so 1 over c squared times 2, t minus sine t, and x of t is 1 over c squared, 1 minus cosine of t. And this is called a cycloid curve. And in case you probably might have seen this in the in calculus 2. What's the cycloid? I mean, the cycloid is sort of, if you roll a ball, I mean like a wheel, where one point on the circumference is marked, so you kind of roll it this direction. And then when it gets to, the marked point is on top, right? From here to there, this is what a cycloid looks like. And it keeps going like this. It's what you see on a bicycle at night, if the bicycle had like a bright spot on its circumference, which of course it doesn't. It has somewhere in between, but halfway or some. In which case it would be sort of a cycloid, but slightly different. Okay, so that's the shape, and I don't think there is actually an explicit function that you could describe this. So the best way to represent the cycloid is through this parameterization. And if you invert this and you put it sort of on the vertical plane, it would be exactly this shape here. So a portion of this is how you get from a point A to a point B in least time. Okay. So this is sort of a famous variational problem. and it was of course solved. I mean, this, I don't know, 16th century. So it's a long time. 17th century. It's a long time ago. But it kind of gives you a sense why. I mean, why is the shape like that and not not like steeper or less steep, right? Any less steep, if you start less steep, you're going to spend more time. More steep, you're going to spend less time, but you're going to go a longer distance. Okay. Let me just state one more. So one more application, minimal surface of revolution. And by that I mean the following. So the following problem, to find, so given two circles in the vertical plane that are like this. So you have, they're kind of a line on a horizontal line, but they're vertical circles. So in effect, you have two radii. One is here, and you have another radii. And I think they use X for the horizontal direction. So you have two circles like this with possibly different radii. What you'd like to do is you'd like to find a surface of revolution. So what's a surface of revolution? It's basically a path between those 2 points that is then rotated around the x-axis, and it gives you a surface. Of course, this would be the symmetric, so hopefully I can draw it like symmetric. Okay. So a path like the full red path here would determine the surface of revolution by rotation about the x-axis. So the question is, find a path. Find the surface of revolution of minimum area. Okay. And it's very quick to kind of write that down. The surface area of such a surface of revolution is given by the integral from a to b. There's a 2 pi u of x. So if u is actually just the displacement from the of the top at location x, or if you want, is the radius of the cross section at location x, times the square root of 1 plus u prime of x squared. So you want to minimize this under the conditions. So u admissible means u of a is a and u of b is b. Okay? So again, it's a variational problem, standard variational problem. So If you give me 2 more minutes, then I can write the Euler-Lagrange equations. So let's see, I have f. I'm going to kind of go back to that lambda and xi. So the integrand is just lambda square root of 1 plus xi squared, right? Lambda stands for u and xi stands for u prime. So the Euler-Lagrange says f lambda minus derivative with respect to x f xi equals 0. Yeah? What's f lambda? Lambda is just appears just there, so it's just the square root of 1 plus xi squared minus derivative with respect to x what is f xi? Lambda xi over the square root of 1 plus xi squared. Okay? So, of course, you have to replace xi with u prime and lambda with u. Okay? Now the problem is how can you write a differential equation for u? If you kind of take this derivative inside, you're going to get u double prime, right? And which is nowhere else. And that's sometimes okay. I mean, there's nothing else to do. But in this case, we can kind of, if we multiply by u prime, we can actually make a perfect derivative, just like in that previous, like earlier today. Right? Since f is independent of x, it only depends on the u and u prime, or lambda and xi. And this means what was the analog form, the similar form? It was f minus u prime f, well, u prime was xi, f xi, so u prime xi equals 0. And of course, this was evaluated at u of x, u prime of x, u of x, u prime of x. So in the end, you can just write what this equivalent form is. So the thing inside, f was lambda, so that's u of x square root of 1 plus u prime of x squared minus u prime of x times the partial of f with respect to the second variable, that was u of x, u prime of x over the square root of 1 plus u prime of x squared equals a constant. So this is a constant thing, right? So if you suppress the variable, I mean the argument x, it's just going to look like this: u 1 plus u prime squared under the square root minus u prime squared over the square root of 1 plus u prime squared equals constant. Okay? When you simplify this, well, how do you simplify it? Just write the common denominator. Look what you get. Well, u times 1 plus u prime squared, right? It's common denominator. Minus u times u prime squared in the numerator over the square root, and the denominator is constant. Yes?
You lose the u prime
No, I put it squared. So this and that is the square of u prime. And you can see that that thing cancels, so it's only u over the square root of 1 plus u prime squared equals c. That's a great simplification, right? Because now there's no u double prime. Of course, you have a constant which you'll have to find from kind of boundary conditions, right? But if you keep doing this, then you're going to get square root of 1 plus u prime squared equals c over u. No, u over c, excuse me. 1 over c times u. So the 1 plus u prime squared is 1 over c squared u squared. So u prime squared is 1 over c squared u squared minus 1. So u prime is the square root of, plus or minus the square root of u squared minus c squared over c squared. So if you do separation of variables, you're going to get something like this. And after integration, so this is x 1 over c plus another constant, let's say d. And I'm not going to go through integrating that expression. I mean, there is, well, you can do through various changes of variables, but ends up being cosine hyperbolic inverse of u over c. So in the end, u over c is the cosine hyperbolic of 1 over c plus d. So u of x is c times cosine hyperbolic 1 over cx plus d. This is what ends up looking like. So it's like that. Cosine hyperbolic, remember, it's like an even function. Of course, it's translated. It's not really centered at the origin. It's not symmetric with the vertical axis. It's a little bit translated, and that's because if you have two things that are not the same, I mean not the same height, you're going to have some probably shifted closer here than here, right? With a minimum. So that's part of it. So if you kind of extend this, you would go like a cosine hyperbolic, right? But it's shifted. If the two circles have the same radius, then it would be a symmetric. It would be no d there, right? Okay, and the story is that there is actually, it doesn't, there's no solution for all possible radii, and also the distance between the two circles. So to find C and D, one needs to use the values of the u at the two endpoints. Okay. And unfortunately, this doesn't have solutions always. So depending on A, B, and pretty much the distance between the two circles. B minus A, this may or may not have solutions. In other words, you may not be able to find such constant C and D to satisfy these equations. And this is kind of a nice. I was trying to actually show you a movie, but I couldn't actually make it to work. in which, depending if it's not as much as the values of A and B as it is the distance between the two circles. So if you have two circles that are fixed radius, right? But you kind of move them up far apart, then you can see that this cosine hyperbolic is really exploding quite fast. So you may not be able to actually get it to, to fit this cosine hyperbolic, with those particular values at the endpoints. Okay. This particular surface has a very nice property, which is the minimum area, right? And that's called minimum surfaces, if you want, with this boundary conditions. And all this is saying is that if they're too far apart, you may not be getting a bona fide surface that has minimum area. The minimum area is going to achieved if you have, so if they're far apart enough, then you would have the following. You would have the minimum area is going to achieved by just like a vertical it would be the surface of this circle plus the surface of this circle. Okay, and that has to do with this. I'll tell you after the break. But think about a soap film that wants to be kind of stick to this, two circles, two circumferences. If they're close enough, you can actually make a soap film to kind of, go from one to the other. Whereas if they're far apart, the soap film is going to kind of detach, and it's going to break, and you're going to get actually the you're going to fill this circle, and that's it. And so sometimes you don't have, you have a minimization problem, but it's not sort of the one you're looking for as far as the admissible paths. Okay, so let's take a break. I don't know.